Okay. Hello, everyone. Welcome to this week's ARMA Future Leader webinar series. Today, we are honored to have Dr. Isabella or Ella West to present her work. Ella is working as a geotechnical engineer at WSP USA in their mining stability group. Her focus is on numerical modeling of rock and soil structures for mining applications. Prior to working in industry, she completed her PhD in geological engineering from Colorado School of Mines with a focus on discrete element methods, numerical modeling, and laboratory testing. Her talk today is bounded block modeling for synthetic rock mass modeling. It's a validation of predictive capabilities. So, Ella, the floor is yours.
Thanks so much. Thanks everybody for joining today. So that was a good introduction. I don't need to go over it again, so I'll just get right into it. But before we start, I do want to acknowledge my co-authors on this study, Dr. Gabriel Walton, who is my PhD advisor at Colorado School of Mines, and also Dr. Shankar Sinha, who is also a mining consultant for Equilibrium Mining in India. Also, you can go and read this paper if you want. It's on the journal materials, which is open access, so it's pretty fun. Just search my name or this title, and you can read the entire article for free online. So quantifying the behavior of a rock mass is crucial for many engineering applications. So for example, the oil and gas field would be interested in rock mass behavior for fracking, for example. Civil infrastructure fields need to understand how how rock masses behave for deep foundation applications of large buildings or skyscrapers, or another example would be for road cuts to allow or improve access to mountainous regions. And this is especially true for mining, which is my field. And miners care about rock mass behavior for both open pit and underground mines, where the excavation of ore rock wouldn't be possible without this understanding. So understanding how strong a rock mass is or how it will deform after an excavation or under an applied exterior load allows engineers to make the safest and most efficient designs. So I just used the term rock mass quite a few times in the last slide, so I want to make sure we're all on the same page and define what a rock mass is before we get into the methods and background of this study. So a rock mass is a large-scale rock formation that contains sections of intact rock separated by pre-existing discontinuities. So discontinuities could be things like faults, shear planes, or joints, and other things like that. Specifically for this study, I'm going to focus on joints. So due to the large scale of rock masses, the representative elementary volume is typically on the scale of meters, and this makes quantifying its behavior very difficult. So I'm going to get into the background now of the four main methods for studying rock mass mechanical behavior and their associated pros and cons. So first is large scale lab testing. Large presses or triaxial apparatus like this one shown in this photo, these do exist, but the maximum diameter of these machines is typically about 1 meter, and therefore they won't accommodate rock mass specimens with representative elementary volumes of multiple meters or larger, which is quite common in situ. Additionally, extracting, transporting, and installing specimens of this size is very difficult. Not to mention these tests take a lot of power to run, and there are very few facilities in the world that have an apparatus of this size. Instead, engineers frequently rely on empirical classifications to predict the behavior of rock masses, like some of these more common ones that I've listed here on this slide. A lot of you might be familiar with Geological Strength Index, GSI, by Hook 1994, Rock Mass Rating, RMR, Rock Quality Designation, RQD, or the Tunneling Quality Index, also called the Q system. And these are just some of the more common ones. So these empirical rock mass classifications are often prone to error, since each system was developed using various assumptions about the rock mass, and the misuse of one of these classification systems in a case where it doesn't apply will result in an ineffective design. So many researchers have instead utilized these small-scale rock mass analog laboratory specimens, like in these photos. So researchers ask questions like, how does the orientation of a joint affect the overall behavior of the rock? Other joint properties like the density of jointing, joint roughness, or persistence, like shown in these photos, where the blue highlighted segments are rock fractures, and then the white segments in between are actually intact rock bridges. All of these parameters have been tested in the past using these small scale analog specimens. And this was done to understand how the joint property affects the overall behavior of the rock. So to emphasize this, this isn't necessarily looking at just the shearing along an individual joint and how the joint properties affect that behavior, but this is actually looking at how the overall specimen behaves. So that includes intact rock deformation in addition to shearing along the pre-existing joint plane. So kind of a combination of everything to look at this overall deformation. And that's what I'm going to be talking about through the rest of the presentation. So the trends deduced using these lab scale specimens can then be extrapolated to larger field scale rock masses. In these analog specimens, joints are artificially created so that the joint property in question, like roughness or persistence, can be accurately isolated. And this is really powerful because if we were to just take in situ rock mass specimens straight from the ground, it's not very easy to control the properties of these specimens. How do we really assess how rough the joints are, or how dense the joints are, or their persistence and other properties like that? If we can artificially create these specimens, that means we know exactly what the properties are because we're creating them ourselves, and that allows more control in the laboratory. So one specific study I want to highlight is Alejano et al. 2017, which was the first study to consider more than 1 degree of jointing in these small scale rock mass analog specimens that also contained more than one joint set. So in this study, they performed compression tests on specimens of Blanco mirror granite with 2 different joint geometries. So one geometry is in this picture on the left that contains 1 subvertical and 2 subhorizontal joints. And this is referred to as the 1+2 geometry. And the second geometry shown here on the right contains 2 subvertical and 3 subhorizontal joints. And this is referred to as the 2+3 geometry. So this study provided an important analysis of rock mass mechanical behavior that wasn't previously available in the literature. They quantified the degree to which the rock specimens became weaker, less stiff, and more ductile due to the presence of these pre-existing joints and the increase in degree of jointing between the 1+2 and the 2+3 specimen cases. So I want to note that very few studies on rock mass analog specimens have actually used real rock. And this is simply because of the difficulty of specimen preparation. So take, for example, the simplest geometries here on the left, which are the same as these specimens I just showed you from the Alejano et al. 2017 study. These contain smooth saw-cut joints. But for specimens that are only 5.4 centimeters in diameter, you can imagine that it's actually pretty difficult to consistently and accurately cut these joints, since we want to standardize the locations and the orientations and other properties of these joints. So and imagine too, if we want to test even more densely jointed specimens, it's very difficult to cut these joints. Also, for more complicated jointing, like rough and impersistent joints, the specimen preparation methods are extremely difficult. And to date, there actually haven't been any methods that I've seen in the literature that are able to prepare specimens of this type in real rock. So instead, there have been a lot of studies using analog specimens that utilize 3D printing, or they create the specimens using other synthetic materials like plaster of Paris. But these materials don't have intact rock characteristics like its high strength and brittle behavior. So numerical models are the 4th technique for studying rock mass mechanical behavior, and numerical models can avoid the practical limitations associated with lab testing that I just talked about. And this is because computers can easily simulate joints of any geometry, including the rough and the impersistent ones and other more complex joint patterns. So specifically, I want to talk about synthetic rock mass modeling, which will henceforth be referred to as SRM. So SRM has been used for decades to simulate rock masses. SRM is based on the premise that if a small scale model can be calibrated so that its micromechanical behavior approximates the failure mechanisms occurring at the grain scale in real rock, in addition to matching the emergent material attributes like strength and stiffness, then the model will act mechanistically realistic at other scales, but more importantly, under other conditions, like with the presence of a discrete fracture network. So the issue with the current state of SRM is that it's mostly been used in industry, where these models have resulted in reasonable field scale ground behavior that were in like the right ballpark area. But to date, there hasn't been a peer-reviewed proof of concept to verify this method. And this was the motivation for this study. So I want to summarize all of the background that I just went through. Large-scale lab specimens and rock mass classification systems are not practical for investigating rock mass mechanical behavior. However, small-scale rock mass analog specimens are a good way to investigate trends in how jointing affects rock mass behavior, despite the limitations associated with specimen preparation that I talked about earlier. And numerical modeling is an up-and-coming technique for rock mass behavior prediction, but there's still a lot to be learned about the predictive capabilities of numerical modeling of rock mass, specifically SRM. So with all of this in mind, this research project uses the concept of small-scale rock mass analog specimens to ultimately investigate rock mass mechanical behavior. So specifically, lab-scale specimens, the analog specimens of rock were simulated using numerical modeling. And the reason for simulating the lab scale specimens was to ultimately use available laboratory data to verify the predictive capabilities of the numerical model. And this is something that hasn't yet been done regarding SRMs. So the main research question was, can bonded block modeling be used in synthetic rock mass models to predict rock mass mechanical behavior? So I'd like to note too that for this validation of SRM, we've only looked at the addition of a discrete fracture network, and we didn't look at the upscaling from the lab to the field scale. So that's one of the major limitations of this study. So this slide outlines the 4 main research steps as part of this study. So like I talked about earlier, laboratory studies were performed on both intact and jointed rock. And this data was actually taken from that Alejandro et al. 2017 study that I talked about earlier. Next, a numerical model of the intact rock was generated and calibrated to the intact laboratory data. And I'll talk about the details of the model generation and calibration process a little bit later. After that, joints were added to this intact calibrated model in the exact locations and orientations as the joints in the jointed specimens. And finally, the results of simulations like triaxial and UCS test simulations on these jointed models were compared back to the laboratory results on the same jointed specimens. So it's in this 4th step here where the predictive capabilities of this numerical model that was developed can be assessed. So this is the numerical model that was used for this research. It's a discrete element method model. So these polygons, which are outlined by the black lines, these are continuous elements which are able to detach from each other and allow fracture formation. So to show you what this looks like, I'm going to begin kind of an example simulation on this model. So this is a unconfined compressive strength UCS test. So no confinement on the sides, and we're adding a load to the top of the model, and the model's fixed at the bottom. So you can follow along with this simulation in the stress strain plot on the left. So you can see that as stress is increased on the model will begin to dilate, and this is mostly going to be in the radial direction due to the formation of microscopic fractures. Fracturing initially occurs through various locations of the model, but eventually the fractures will begin to coalesce into a global failure surface. So this grain scale deformation is akin to the failure processes in real rock. I just threw a picture of a real rock failed under UCS conditions here for your viewing. So you can see that the fractures formed in this real rock specimen look quite a lot like the fractures formed in the model. So we see that kind of axial splitting, the axial oriented tensile fracturing, and we see that in the model as well. And this is not a coincidence. So specifically, this model that I just showed you is a bonded block model, which will henceforth be referred to as a BBM. So in BBMs, material is broken into continuous elements, which are referred to as blocks. So in the case of rock, these blocks can actually represent individual mineral grains, but it doesn't have to. Blocks interact then with adjacent blocks via contacts. And you can think of a contact as a stiff spring that connects these two discrete blocks. So the deformation of a single block is induced by exterior stresses on the element and are governed by input parameters like stiffness and strength, and these are referred to as block properties. The interaction of a block with an adjacent block is also governed by input parameters like stiffness and strength, and these are referred to as contact properties or contact input parameters. Different blocks can also be attributed to different minerals. So for example, 1, 2, and 3 could be like quartz, feldspar, and biotite. Unique block properties can then also be assigned to each material type. So stiffness and strength 1, 2, and 3 can be different values. And the corresponding unique contact types between each of these different blocks can also be attributed different contact parameters. So there are two main subgroups of BBMs where the blocks can be modeled either elastically or inelastically. And I found now that I work in industry that we actually use the term plastic a lot. So if you're more familiar with plastic, that's the same thing as inelastic. So elastic blocks require only stiffness as an input, which means that these blocks are able to deform elastically, but they can't permanently deform. So if the load on an individual block begins to decrease and eventually goes back to zero, the block will actually rebound and return to its original shape and size. On the other hand, inelastic blocks require both stiffness and strength as input parameters, and strength parameters can be defined by any sort of constitutive model. So in this specific case, we use the Moore-Coulomb-Taylor criterion, but other things like Brown or any other constitutive model can work as well. So once the stresses on that block reach the strength criterion level, the block will then begin to permanently deform. So this means that even if the stress that's applied to the block begins to decrease, the block will never be able to return to its original shape and size because it's been permanently deformed. So both types, elastic and inelastic blocks, have been used in the literature, and both have been considered for this study. And they both have pros and cons, which I won't get into all of them, but the main one is that elastic block BBMs have significantly lower computational load. But then also inelastic block BBMs have been found by other studies to be necessary to replicate the post-peak behavior of rock deformation. So pros and cons. Okay, so I want to get into the methods of the study now. So the blocks of the BBM were generated to approximate the shapes, proportions, and average diameters of the mineral grains in the real rock. So this BBM is highly heterogeneous. It has 4 different block types: feldspar in pink, quartz in blue, plagioclase in gray, and mica in black. And these 4 block types then correspond to 10 distinct contact types, which are listed here on the right, and you can see them labeled here in this inset. Each unique block and contact type are able to be attributed to different input values for both contacts and block properties. And these input parameters must be determined via a calibration process. So the calibration process means that I carefully selected all of the block and contact input parameters so that the emergent macroscopic behavior of the model approximated that of the laboratory data. And this calibration process is actually required for all discrete models because the majority of input parameters into discrete models are not able to be directly measured in the lab or in the field. So at this point, I also want to draw attention to the other main limitation of this study, which is that we utilized a 2-dimensional model to replicate the behavior of a 3-dimensional laboratory specimen. And so the main reason for doing that is that 3D BBMs at this point have a prohibitively high computational load, especially when the goal was to replicate the grain scale structure of the rock, which is down to the millimeter scale. So it wouldn't have been possible to use a 3D BBM for this study without it taking much longer than I would have wanted to finish my PhD. But that being said, 2D BBMs are very common in the literature, and they've been found through rigorous studies and analyses that they're very capable of replicating micromechanical fracturing of rock. So that's why we went with a two-dimensional model. Okay, so as I was talking about the calibration process, I selected all of the input parameters to carefully match the intact model to the intact lab data. And so in these next few slides, I'm going to show you the results of this calibration process. So this is me showing you that the calibration that I did is good. So in all of these figures, we've got confinement plotted here on the x-axis. So I ran 6 different confinement level tests, compression tests. First, there's a UCS or an unconfined test here with 0 confinement. And then I ran 5 different triaxial simulations ranging between 2 and 12 megapascals of confinement. And so in all these plots, the lab data is plotted as the black circles, and then the results of the calibration for the elastic block BBM are plotted as the red triangles, and the inelastic block BBM results are the blue squares. And then we've got some Cook-Brown fits just to help us look at trends. So this right here on the left is plotting the peak strength of the models. You'll see that I was able to calibrate the model to fall within the approximate middle range of the laboratory data under all confinement levels, with the exception of the unconfined data set. So this was actually done on purpose because pre-existing flaws in the rock, like pores and other like microfractures, actually decreases the strength of the rock. And this is seen much more in the unconfined UCS tests, where these microflaws, they influence the strength a lot more than under higher confinements when these flaws are able to be closed. So in order to get the correct trend, we actually had to calibrate the model to the upper end of the range of lab data because the model doesn't have these microflaws. The model has 0 porosity and 0 microflaws, so we couldn't capture that behavior. On the right-hand side is a very similar plot, but for dilatancy. So we've got peak dilation in degrees plotted on the y-axis. And again, the model was calibrated to fall within approximately middle of the range of the laboratory data. And this is true for both the elastic and inelastic block BBMs. So I won't talk about CI and CD too much. I don't know how many of you are familiar with the concept, but for those who are, I just threw these on here. We considered a lot of material attributes when calibrating these models, and crack initiation and crack damage thresholds were 2 very important ones. So we wanted to make sure that, again, the models were calibrated so that their CI and CD values fell within the approximate middle of the range of the laboratory data. And finally, I also want to show that we considered the micromechanical failure processes and failure modes of the model as well, in addition to these mechanical material attributes. So this is just the example of the elastic block BBM. We've got the 0 confinement, the UCS case on the left, and the highest confinement, the 12 megapascals confinement case on the right. So on the left, you'll see that this model has failed mostly through axially oriented tensile fractures. So this is akin to axial splitting and spalling, which we see in real life laboratory UCS tests of brittle rock. And I've also tracked the number of fractures failing in tension versus shear in the model. So you'll see that tensile fractures significantly dominate over shear fractures in this model. On the other hand, on the right here, we've got the higher confinement case. You'll see that the number of tensile fractures has come down and the number of shear fractures has come up. And we still have a lot of axially oriented tensile fractures at this point, but they're not coalescing as much. We've got kind of this an echelon stair-stepping pattern and a bit more like global shearing than we did in the lower confinement model. And so, it's higher confinement, it's not super high confinement. So this is what we'd expect. I also want to note that I'm showing the models here right on the cusp of failure. It's right at peak strength. So right as the model is failing, if we were to continue the simulation all the way to residual strength, you'd eventually see these shear bands coalesce into a large shear band that goes from one side of the specimen to the other, which is what I'm sure you all are used to in the lab. Okay, so in these last few slides, I just showed you all that the calibration I did was good. So now that I calibrated this intact model, the next step is to add the 2 different fracture geometries, so the 1+2 and the 2+3. And I ran these simulations without changing any of the input parameters from the calibration. So no adjustment of input parameters whatsoever. And now we want to see how these two cases of the jointed models behave and how they compare to the laboratory data of the jointed specimens. So this slide here is showing elastic moduli. On the left, we've got Young's modulus, and on the right, we've got Poisson's ratio. So the intact case, again, this was the calibration. So I made sure that the model's Young's modulus was calibrated to the approximate middle of the range of lab data. And then these two, the 1+2 and the 2+3 geometries, these are the predictive validation steps. So without changing any of the input parameters, this is the Young's modulus output of the 1+2 geometry, and these are the Young's modulus output of the 2+3 geometries. So you'll see for both cases, the elastic and the inelastic block BBMs were able to predict the Young's modulus values within the approximate middle of the range of laboratory data for both geometry cases. And this was the same for Poisson's ratio here on the right. Of course, we have a much larger spread of Poisson's ratio values, which is typical for Poisson's, as most of you probably know. But again, this calibration was able to yield these two predictions, which fall within the approximate middle of the range of the lab data. So now I want to show the same idea, but for peak strength. So on the left, we've got the 1+2 joint geometry, and on the right, the 2+3 jointed geometry. So you'll see that both the elastic and inelastic block BBMs were able to predict the strength of the laboratory data within the range up until the higher confinement cases of 10 megapascals and above, where the models slightly underpredicted the strength. However, this wasn't the case for the 2+3 jointed geometry, where both model types were able to predict within the range of laboratory data on the strengths. And so overall, even though these specific confinement cases are slightly underpredicted, the general trend of increasing strength as a function of the confinement has been captured, and so we're very happy with these results. So we also looked at crack initiation thresholds as well. So you'll see that both the elastic and inelastic block BBMs were able to predict CI values for the 1+2 jointed case, and same thing for the 2+3 jointed case. Both model types were able to predict the values. I'm going to start to sound like a broken record, but this is also crack damage thresholds if you're interested. We see the same slight underestimation of crack damage thresholds for these two higher confinement cases in the 1+2 geometry, which makes sense since we saw a slight underprediction in the strength, and CD and strength are related. But also we didn't see that in the 2+3 jointed case where the predictions were quite good. And finally, also want to show you dilatancy. Both model types were also able to predict the dilatancy of both model geometries, 1+2 and 2+3. So overall, the results were very good, better, I think, than we were even expecting. And I just want to summarize everything now. So the bonded block model was calibrated to reasonably replicate grain scale fracturing processes in real rock, and that gave it its predictive capabilities, meaning that bonded block models can predict rock mass behavior under conditions different from which they were calibrated. So intact BBMs can be calibrated at the lab scale and then applied to other jointing scenarios using numerical modeling. This research has verified the concept of the synthetic rock mass models. So that's good news for all of the past studies that have used this concept without such a rigorous verification. So one important caveat to these findings that I want to highlight, and I actually did highlight them in the red font, is that this research has only shown these statements to be true for this one specific rock, Blancomere granite, which is a highly brittle rock. And this was actually the motivation for another chapter of my thesis where I replicated this same study, the entire process, including the laboratory testing campaign, on a less brittle rock. But I won't get into that today, maybe a topic for next year. And so just to tie everything back in together, I mentioned a couple times now that the major limitation associated with laboratory testing of the rock mass analog specimens is the difficulty of preparing the more complex specimens like rough and persistence or the heavily densely jointed specimens. So this verified the predictive capabilities of the Blanco Mirror Granite BBM, which provides us with a unique opportunity to now test these more complex using the model. And this is another thing that I did for my PhD research, and definitely won't get into that today. But yeah, I think this study has opened up a door to be able to test a lot of things with certainty that people haven't been able to in the past. So yeah, thank you very much. And if you have any questions, let me know.
All right. Thank you, Dr. West. For the participants, please feel free to unmute yourself and ask questions. If not, we can first go through the questions in the chat. So Ed asked a question. He said, "Ella, what is different about the BBM you used in and the UDEC or 3DEC? Also, I missed part of your talk, but did you adjust your model in some manner to compensate 2D models for 3D data?"
Sorry, can you repeat that?
Yeah, so I think you can also see the questions in the chat. So the
Okay,
first
yes,
question is
interesting.
the different about the BBM you used and UDEC and 3DEC, if you're familiar with those.
Gotcha. Yep. So all of the models that I used for the study were UDEC two-dimensional. So that was one of the limitations I talked about earlier. It can be done. Bounded block modeling has been done for a lot of studies in the past using 3DEC, a three-dimensional model. But like I was saying, those models have much coarser grain structures. So the point of this study is that I really wanted to replicate the grain structure of the rock accurately. So we have, plagioclase, quartz, feldspar, and mica crystals that are on the millimeter scale. At most, they're about 3 millimeters, like the quartz and the plagioclase are 3 millimeters. The micas get down to even like 1 millimeter or like a little smaller than that. So to replicate the true size of that crystal structure, we had to do a two-dimensional model. Otherwise, the computational load for a 3D model of that with that fine size blocks would be just absorbent, and we wouldn't be able to finish the study. Well,
Right.
maybe in like a decade or something. But this is common too. And actually, for my second study, I was saying I replicated this, but for a less brittle rock, and the crystal size of that rock was like 0.1 millimeters. And, I tried to create a grain structure of that size, and it was going to take like 2 months to run one model, and, only have so many years for a PhD. So in the end, we ended up increasing the size of the blocks by about 1 order of magnitude. And this is very common. A lot of other studies have done this. So they don't actually replicate the grain scale crystal structure per se, but they want the blocks to be small enough so that the fracturing processes that we see in the rock are still occurring in the model. That's the most important part. But for this model specifically, we wanted to match everything. We wanted to be as calibrated as possible to avoid any extra variables that might be like if the validation, if the prediction didn't work out, we wanted to be sure that the reason was that bounded block modeling just isn't suitable for prediction of synthetic rock mass models. And in that case, like if we had other variables that weren't matching exactly, then we can't necessarily claim that. So we wanted to match everything pretty much exactly. So we couldn't use 3DEC, but there are other studies, as I was saying, so I can send you some, not by myself, but other people that have used 3DEC before.
Yeah, great. I think the second part of the question is there some way to compensate the 2D model for 3D data? Yeah, I kind of have the same question because, if you have a two-dimensional model of these blocks, you only have limited ways of slipping between the blocks, but in 3D you have more directions to slip against. So how do you address this?
Yeah, absolutely. And this is a limitation that we couldn't really get around. And that's why I think a future a future next step for this, this general topic is to try to replicate this in 3D with potentially with a brittle rock that has much coarser crystal structure than the one here, maybe even like 10 millimeter crystal structure or something like that. So yeah, we didn't adjust anything to consider the 2D to the 3D, but we did quite a rigorous literature review, and there's been dozens and dozens of bonded block 2D bonded block models in the past in the literature that we've reviewed, and some very intense studies that have looked at like the micromechanical fracturing processes and the ability to replicate post-peak behavior and matching to laboratory data. And all of the studies are very positive in that the 2D bonded block models are capable of replicating the specimen scale behavior. And so because of that, we felt confident that the 2D model would be able to replicate the 3D specimens.
Okay, great. Anyone else? If you have, actually, Andrew Corkum, he has a question. If you have published journal papers from the work, I
Yes.
believe you showed one in the beginning, right?
Yeah, I was gonna say I can try to go all the way back here. This paper specifically is published open access, so yeah, if anyone is interested, a lot of
Nice.
slides. If anyone's interested in reading it, you can go ahead and search this title or my name, West et al. 2024, and you can read it open access. So super exciting. Yeah, I have all but one chapter of my thesis published so far. So if anybody is interested in the papers, send me a message or an email or LinkedIn or whatever, I can get them sent to you. So yeah, there's this study that I did here that I just presented. And then as I had mentioned a couple times, I repeated this study for a less brittle rock and compared the results. So looked at the ability of the bonded block model to replicate brittle versus more ductile or a little less brittle rock behavior. And then I also then used this study that I just presented and added a bunch of different discrete fracture networks with different properties like testing persistence, orientation of joints, roughness, things like that. And looked at, comparing, like this has been looked at in the literature before, and seeing if like this model was able to see the same trends, but then also we were able to use the model to test more complex jointing that hasn't been tested in the literature as well. So we kind of like confirmed some results and presented some new results. That paper was published recently, so I can send that to anybody as well if they're interested.
That's great. That's great. Oh, I see Professor Zimmerman is here. Professor Zimmerman, congratulations to you on the new book.
Yes, thank you very much. Thank you. I hope you can hear me. Did I unmute myself?
Loud and
Yes.
clear. Yeah.
Okay.
Do you have any questions?
No, I would like to say it was an excellent presentation. I really enjoyed it, and I'm looking forward to reading your paper in more detail. I hadn't seen the paper yet. So
Thank you.
work. Very good.
Great. Great. So there's another question in the chart in the chat. Is there a takeaway here about the applicability of Hogan-Brown stress model to jointed rock masses as a function of joint material scale?
Good question. Yeah, so I did some of my plots here. I put some Hook-Brown curves, so I'm not sure if that's what spurred this question. But we didn't do any rigorous analysis on Hook-Brown for this study. Mostly, I just fit these curves here as a way to, guide the reader to see the trend in increase in stress as a function of confinement for this specific study. But this is actually something that me and my advisor, Dr. Gabe Walton, are still working on. So we've used this bonded block model that I just presented here, the calibrated predictive model. And we're working right now on running even more simulations, and we're going to look at the applicability of geological strength index and, obviously as that relates to the Hook-Brown criterion for rock masses, given that we're able to now kind of analyze so many different joint properties, some that may or may not be considered in GSI, or they're considered intrinsically, but not as rigorously as it would be, as we would want it to be to like easily attribute a GSI value. So this is in the works. Can't share any secrets yet, I guess. And then in terms of material scale, yes, another great question. So we collaborate a lot with Dr. Alejano in Spain, and his lab has actually been working on this topic. So they're the masterminds behind the jointed specimens. You know, they are able to saw these guys really, really nicely. So they are working on, and I think they actually published recently, so I can get you that paper if you're interested. They did a study, pretty sure published recently, where they did these 1+2 and the 2+3 joint geometries, and they looked at 3 different sizes. So they've got these specimens, which are 5.4 centimeter diameter, and then they have a larger one. I can't remember exactly the size. And then they have an even smaller one. I think it's about 3 centimeters diameter, or 2.5 maybe, which is very, very hard to saw even like 2 joints into those specimens, but they've done it. So they're great. And they looked at scale effects. So I can give you that paper if you're interested. Just shoot me an email or a message.
Okay.
Question?
Yeah, our chat is getting very lively. There's BT Lee who asked, thanks for the presentation. For the stiffness, what is the range of the stiffness values? Did you put shear stiffness also? If there's any difference in stiffness for the joints with or without cement?
Yeah, super great question. Yeah, so let me move forward to this slide. Yep. So we have 10 different contact types here. They're the ones listed here on the right and labeled in this inset. So each pairing of blocks have a corresponding contact, and their contact properties can be different. So they have stiffness values, and that includes joint normal and joint shear stiffness. And then they also have strength values. So we specifically use the more Coulomb failure criterion. So they've got cohesion and friction angle, and we did strain softening too. So peak and residual cohesion and friction angle values. So they all do have cohesion, and residual cohesion goes to 0. So I think it ranges between maybe 2 or 3 to maybe 35 megapascals for the cohesion, the peak cohesion. So once the strength of the contacts is reached based on the cohesion and the friction angle, then it degrades to residual values where we have I believe the residual cohesions were all, yeah, the residual cohesions were all 0, and I believe the residual friction angles were about 5 degrees for the contacts, whereas the peak friction angles ranged from, you're testing my memory here, it's been a couple years since the PhD. I think they were like about 20 to 50 degrees, depending. So like a quartz-quartz contact, for example, will be very strong, whereas a mica-mica contact will be soft. And we've got like kind of a range. And so we took these values, we took the starting input values from some of the other bonded block models presented in the literature, and then we adjusted the values within a reasonable range during the calibration process. And so the stiffness values, these are very high because these are contacts between like lithified crystals, right? So they're very stiff. They're on the order of 10 to the 15 pascals. And then for these the jointed models here, the big joints are much less stiff, and they don't have any cohesion or tensile strength or anything like that. And actually the friction angle input for these large joints was measured directly in the lab as 30 degrees. Because the point of this study was that we calibrated the intact model, but we didn't want to calibrate any of the input parameters for these joints. So that's another reason we used smooth joints, because they've got 0 cohesion, 0 tensile strength, and we were able to directly measure that friction angle in the lab. Is that all the whole question, I think? Yeah, and yep, shear and normal stiffness values for the contacts.
Okay.
Okay, it's better to say it in the microphone, sir. So the stiffness value by itself is, I think, is kind of a range. It's not super too high. So I think it's 20, 40. 40 gigapascal, fine. Is there any relationship between the normal stiffness and shear stiffness in these cases? You give the ratio in between, or you give individually different the shear stiffness in the model?
Yeah, that's a good question. So that's part of the calibration process. So yeah, so the calibration process, actually the first thing that I found is the best to start with for calibration is the stiffness parameters, because the stiffness parameters really only control the linear elastic region of the overall deformation of the specimen, the simulated specimen. So Young's modulus and Poisson's ratio. So I started the starting stiffness values I took from the literature for similar contact types. So there was another BDM that had the same kind of composition like feldspar quartz, mica and stuff like that. So I took those starting values and whatever Young's modulus came from that, I compared to what the Young's modulus was of my rock, and whether it was like, if my model was over predicting or under predicting, I would, alter the stiffness values accordingly. So the overall value of like the magnitude of stiffness controls the Young's modulus, whereas the ratio between the normal and the shear stiffness values controls the Poisson's ratio. So I actually found that it's easiest to start with Poisson's ratio. So find the correct ratio between normal and shear stiffness, calibrate the Poisson's ratio, and then from there you can change the overall, like you want to keep the ratio the same, but you can increase and decrease the magnitude of the stiffness values to match your Young's modulus while maintaining the same ratio to maintain the Young's modulus value. So that was actually the starting place for calibration. And then from there, I moved on to calibrating cohesion, friction angle, other properties like that, which control past the linear elastic region. So those control CD, peak strength, and post-peak behavior and things like that.
Okay, got it. So when you get into the plasticity, stiffness is gone, right? Basically.
Oh, what is gone? Sorry.
When you could get to the plasticity, the elasticity is gone. So maybe stiffness value could be gone for the.
Yeah, like it doesn't contribute, you mean?
Yeah.
Yeah.
The reason I ask is this is a very interesting study because I just got my PhD degree in UT Austin in geological geomechanics for the natural fractal pattern development, and then I use the stiffness similar values for the pattern development, and looks like this can give some details in the code. I use the DDMs a little bit different, but I use it really and those Itasca software, and this looks very similar, so I can apply some of these for the detailed study of the natural fracture development. But thank you. I need to read your paper a little bit details.
Yeah, that sounds
Yeah,
cool.
yeah.
Send me a message and we can chat
Sure,
if you're
yeah.
interested.
Okay, thanks.
Okay, Ella, so if we want to use this model, is that built in UDEC already, or it's just a bunch of data set we need to apply into UDEC? How would we implement?
Yeah, so there's a code that's set up to run the simulation, although like theoretically, if you have your own code in UDEC to run a UCS or a triaxial simulation, you can just use the same input parameters as me and it should be replicated. One caveat is that I started my PhD like 5 or 6 years ago, and so I actually used UDEC version 6 and now they're up to UDEC version 7, and the time stepping algorithm that Itasca uses changes between, updates, between large updates at least. And so the calibration will not be valid in UDEC 7, most likely. I haven't actually tested it, but this happened to a different PhD student in my lab where, he calibrated on an older version and then updated and had to recalibrate because the time stepping algorithm was slightly different. So you can still download UDEC 6 from Itasca's website, but yeah, one caveat there. So eventually my model will become obsolete as time goes on, but we're trying to get all of the studies out that we want to use with it now.
Okay, great. Well, if we don't have further questions, I think we can adjourn today. Just remind you, everyone, that the next Future Leader Talk will also be hosted on a non-standard time because the speaker is from Australia. Dr. Kumari. So yeah, just pay attention to the notifications, and we will see you in 2 weeks. All right. Okay. Bye,
Thanks,
everyone.
everyone.
Nice day.